If you haven't skipped anything, then you've just learned about terrain, drawing text, animation, and collision detection. And we're going to see a program that uses all of these to make sure that we understand everything. Let's take a look at the program for this lesson. Here it is. It's a bunch of blocky-looking guys walking around a terrain, and they're bouncing off of each other as they walk, if you look carefully. And this is the program that we want to make. So let's just do a rundown of the code and see if we can understand everything. First of all, we have some constants. We have this constant right here, pi. I'm not sure what exactly this was when I made it. 3.14159, I don't know where I came up with that. And I guess if I spelled it P-I-E, that would have made sense, but pi, that's just a Greek letter. But anyway, just kidding. Yeah, that's pi. And then we have the number of guys that are walking around. We have this variable right here, which indicates the width of the terrain after we scale it. We have this variable right here. And if you remember from the lesson on collision detection, what we did was we alternated between advancing all of the balls by a particular interval of time and handling collisions. And we're going to do the same thing in this program. This variable right here is the number of seconds between handling collisions. So 0.01 seconds. We have a function that gives us a random float from 0 to 1. And we have our terrain class, which is exactly the same as the terrain class from the terrain lesson. So all of this code right here, you've actually seen this exact same code in a previous lesson. Same thing with this load terrain function. We've already seen this. It loads a height map into a terrain object. Then we have this height at function, which is new. It returns the height of the terrain at a particular xz coordinate, and this xz coordinate can be a decimal. So it gives us the height of the terrain in the middle of a grid cell, for the most part. And what we're going to do in order to figure out the height is we're basically going to take a weighted average of the 4 grid points around the particular xz coordinate. And if you remember, actually the way that we drew the terrain is we divided the grid cell up into 2 triangles. So the height for that particular point, xz, the height that you would get based on how we drew it will actually be a little bit different from the height that this height at function will return. But if the terrain is sufficiently smooth, then it won't really matter too much anyway. So first of all, we want to make sure that xz lies within the bounds of the terrain. So if it's too far outside of the terrain, then we just set it to be at the edge of the terrain. Then we figure out a few variables right here. We have left x and out z, which indicate the grid cell in which this xz coordinate lies. We have frac x and frac z, which are just the horizontal and the, not exactly vertical, but sort of in and out distance from the left x, left z coordinate on the terrain. And these are going to be used in order to determine all of these heights that we need and to take the appropriate weighted average. Then we compute the 4 heights that we need, the 4 heights surrounding the xz coordinate, and we return a weighted average of all of those 4 heights. And you can take a look at exactly how this weighted average works. Then we're going to have our guy class right here. And for our guys, we're going to have their own special step and advance functions inside the guy class. And guys are going to be animated basically by advancing their state in small intervals of time. And that interval of time will be the guy step time constant, so 0.01 seconds. Now, for the guy class, we have a few fields. We have an MD2 model object, which represents the model of the guy. We have the terrain on which the guy is walking. We have a scaling factor for the terrain, which is going to get the terrain to be terrain width units wide. We have the x and z coordinates of the guy. The height is just figured out based on the height of the terrain at particular xz coordinates. Then we have this animTime variable, and actually I made a couple of changes to the MD2 model class. Let me show you over here. We used to have an advance method in the MD2 model class which would advance the state of the animation. But since we have a bunch of different guys, we're actually going to have all of the guys be at a different state in the animation. So I got rid of that advance method, and instead of that we have, for the draw function, the draw method, we have a parameter, time, which indicates the state of the animation that we want to use. So that's what we're going to be doing in order to make all of the animations be at different states. And this animTime field is basically the position of the animation, the position that we are in the animation. Then we have this radius 0 field, which is roughly the radius of the guy. We're going to treat all of the guys basically as cylinders for the purpose of collision detection. And also this radius 0 field will enable us to determine exactly by what amount we want to scale in order to draw the guy. Then we have a speed field, which is the speed at which the guy is walking. We have an angle, which is the direction in which the guy is walking. And an angle of 0 indicates the positive x direction. An angle of pi over 2 indicates the positive z direction. So it's kind of like how we normally think of angles on the xy plane, although technically we're dealing with the xz plane. Then we have time until next step, which is the amount of time until the step function is next going to be called. The step function which advances the state of the guy by guy step time seconds. Then we have this field is turning left. Actually, all of our guys are going to be turning very slowly while they walk, and they'll either be turning left or right. This is turning left tells you if they're turning left. We have a variable time until switchter, which is the amount of time until the guy changes which direction he's pointing. So they'll be changing from turning left to turning right continuously. Then we have a step method, which is going to advance the state of the guy by guy step time seconds. First of all, we're going to handle all of this changing direction stuff, this time until switchter variable and the is turning left variable. Then we're going to compute the maximum x and z coordinates for the guy. And this is just basically the width and the length of the terrain minus radius 0. Then we're going to update the x0 and z0 fields to make the guy walk forward. And right here we're calling velocity x and velocity z. Let me just scroll down to those methods. They're down later in the class. They're actually pretty straightforward. They just take the angle at which the guy is walking and the speed of the guy, and they figure out the velocity in the x and the z directions. So those are those two methods. And let me scroll back up to where they're used. So here we go. We're increasing the x-coordinate by velocity x times guy step time, the amount of time by which we're stepping. Then we want to make sure that the guy hasn't exceeded the edge of the terrain. So we're going to have this Boolean hit edge, which is whether the guy has hit an edge of the map. And if he has hit one of the edges, we're going to place him exactly at that edge. So these if statements right here will take care of that. Then we're going to make the guy rotate. We're going to make him turn while he's walking. And to do that, we just have to alter the angle variable. And what we're going to do is if the guy has hit the edge, we're going to make him turn really quickly, so that way he's no longer facing the edge. So if he has hit the edge, we're going to change the angle by 0.5 times the speed times the amount of time by which we're stepping, and either decrease it or increase it depending on whether we're turning left. If we haven't hit the edge, instead of multiplying by 0.5, we're going to multiply by 0.05 because we're not turning nearly as quickly. And once we've adjusted the angle, we want the angle to remain between 0 and 2 pi, so that's what these two while loops right here will take care of. Then we have our constructor for the guy class, which initializes a bunch of fields, and it sets some of them to be random values, actually. It sets the radius, the position, the speed, whether they're turning left, the angle at which they're walking, and the amount of time until they switch directions, all to be random values. Then we have an advance function, which is going to advance the state of the guy by a particular interval of time. And that'll basically just do two things. It'll increase anim time, the state of the animation for the guy, and it'll call step a certain number of times. So, first of all, we're taking care of anim time. We just increase it by an amount that's proportional to the amount of time by which we're stepping, proportional to the speed, and inversely proportional to the size of the guy, because if he's smaller, we want him to basically look like he's walking more quickly relative to his size. And then we just have right here where we make sure that anim time lies between 0 and 1. Over here, using this while loop, we're going to take care of calling step the appropriate number of times. And that's our advanced method. We have a draw method, which is going to draw the guy. If the model happens to be null, then we don't want to do anything. And otherwise, we're going to figure out a scaling factor, which is just equal to the radius divided by 2.5. Actually, this divided by 2.5 right here, I just found out by trial and error. Then we translate to the position of the guy using his x and z coordinate, and also using this y function right here. Let me just scroll down to that really quickly. And here it is. It just uses the height at function in order to figure out the vertical position of the guy. It's fairly straightforward. Then we have, in addition to this y coordinate, we're actually going to add a little bit to it, because because y gives us the y coordinate of the bottom of the guy, we actually need to go up a little bit more to be at the center of the guy. Then we have right here a rotation in order to make the guy facing the appropriate angle, the angle at which he's walking. And actually we're going to have to take 90 minus the angle, because if we had an angle of 0, then that would correspond to the positive x direction, whereas a rotation of 0 would make the guy look like he's moving in the positive z direction. So this 90 minus just takes care of converting from our angle to a rotation. Then we set the color to be white so that we don't do any kind of weird color applied to the model. Then we do a couple of rotations to make the guy facing the right direction. That's because in Blender, when I made him, he was sort of pointing the wrong way that I happened to do it, so I'm just going to fix it by doing a couple of rotations. Then we scale by the scaling factor, and we call the draw method on the model. And again, we pass this anim time field to it to indicate the position in the animation that we want to draw. Then we have a few more methods. We have x, which returns the x-coordinate of the guy, z, which returns the z-coordinate. We've already seen y, velocity x, and velocity z. And we have a radius method, which returns the radius of the guy, a walk angle method, which returns the angle at which the guy is walking, and we have a bounce off method. And this method is going to be useful for handling collisions. It's basically going to make the guy alter his direction when he bounces off of another guy. And the way that this method operates is pretty similar to the way that the bouncing functionality worked in the lesson on collision detection. Basically, we're going to find the direction between the two guys, and we're going to subtract twice that from the velocity, sort of. But this is a two-dimensional problem, so we do need different code. So we compute the x and the z velocity. We compute the displacement from this guy to the other guy, and we make sure that it's normalized, that we divide by the magnitude. We find the dot product of these two vectors, the velocity vector and the direction vector, and we take twice this dot product times the direction vector and subtract it from the velocity. And once we have this, new velocity, this adjusted velocity, we need to find out the direction in which it's pointing. If both of the values happen to be 0, then there's actually no direction, so we're just not going to alter the angle. But in the normal case, which normally not both of these will be 0, we're going to find out the direction of Vx, Vz, and we're going to use the atan2 function, which is a C function, and it just returns an angle in radians given an x and a y given x and y components of a particular vector. So the first parameter is actually the y component, and the second parameter is the x component. And just by calling atan2, we're going to figure out the new direction that the guy should be pointing now that he's bounced off of another guy. And that's our guy class. Now we're going to move into some collision detection stuff. We're going to start with a guy pair structure, which stores a pair of guys, and we're going to be using this to indicate potential collisions. Now we're going to be using a quad tree for this program, which is the two-dimensional analog of the octree we used in the collision detection lesson. So we have a few parameters over here. We have the maximum depth of the quad tree. We have a couple of constants which tell us when to either divide or undivide a particular node in the quad tree. And here's our class for the quad tree. And it's kind of the same idea as the octree we've seen earlier, but I'm going to run through all of it just to make sure that we still understand all of this. We have a few fields indicating the rectangle which this quad tree spans. We have center x and center z fields, which are just the center of that rectangle. We have a two-dimensional array of quad tree pointers indicating the children of this particular node, if there are any children. Then we have a has-children field, which indicates whether there are any children. Again, this node will have children if we needed to divide it up a little bit more in order to sort of divide up the problem of finding potential collisions. We have this guys set, which, if this has no children, it'll store all of the guys in this particular node. We have the depth of the node, and we have the number of guys in this node or in any of its children. Then we have a file guy method, which is going to either add or remove a guy, depending on whether add guy is true, at a particular position to all of the children of this node. So that's what this method right here is going to take care of. It's going to run through, find the children in which this guy belongs, and if add guy is true, it'll call add. If it's false, it'll call remove. Then we have a method haveChildren, which is going to take care of splitting this particular node whenever we have to split it. And what we're doing is we're just going through each of the x and z directions, and we're constructing a new quad tree for we're constructing 4 new quad trees because we have 4 new children. And then we're going to go through all of the guys in the guys set, and we're going to call file guy on them to add them to the children of this node, and then we're going to clear the guys set because we no longer have any children. The guys set isn't really used when we have children. And we set has children to be true. Then we have a collect guys method, which finds out all of the guys in this node or any of its children and puts them into a particular set. So if this has any children, we're just going to call collect guys on all of the children. If it doesn't have any children, we're going to go through the guys set and put all of the guys in there into this set up here. Then we have a destroy children method, which is going to undivide a node whenever we have to. It calls collect guys in order to get all of the guys in the children, or in any of the descendants, really, and put them into the guys set. Then we just delete all of the children. And we set has children to be false. Now we have a remove method, which removes a guy at a particular location, and What this does is it decreases the numGuys variable. It calls destroy children if appropriate, so if the number of guys has gotten to be too low. Then, if there are any children, we just use file guy in order to figure out which children this guy belongs in and remove them from those children. If this doesn't have any children, then we just erase the guy from the guys set. After that, we have the constructor for the quad tree, which initializes some variables. We have the destructor, which just calls destroy children if we have to. Then we have the add method, which is going to add a guy to this particular node. And it'll do that first by increasing the number of guys. Then it'll call have children if there are too many guys in this, if we want to split it up. And if this has any children, we're going to use file guy in order to put the guy into the appropriate children. If this doesn't have any children, then we're just going to insert the guy into the guys set. Then we have a remove method, which just calls the remove method that we saw earlier, using the current position of the guy. We have a guy moved method, which is called whenever a guy changes position, and this just removes the guy at his old position and adds him at his new position. Then we have our potential collisions method, which determines all the potential collisions between pairs of guys. And if we have any children, we're just going to call potential collisions on all of the children. If we don't have any children, we're going to go through every pair of guys and add them to the collisions vector, collisions being a parameter to this method. So we're just going through every pair of guys. And that's the quad tree class. Hopefully it sort of reminds you of how quad trees or octrees basically work. We have a potential collisions function, which just calls potential collisions on the quad tree. We have a test collision function, which determines whether there's actually a collision between two particular guys. And in order to do that, we need to see, first of all, whether the two guys are closer together than the sum of their radii. And if they are, then we're right here in this part of the if statement. We need to make sure that the guys are walking towards each other. If they're walking away from each other, then most likely they just collided a second ago. Or, not a second, but a short time ago. And we don't want to say that there's a collision. So, after that we have handle collisions, which computes potential collisions by calling potential collisions. It goes through them all and finds out which potential collisions are actually collisions by calling test collision. And for all actual collisions, it uses the bounce off method to make the guys bounce off of each other. And then it increases this num collisions variable. If you remember from the program, let me just run it again. We want to display at the top of the screen how many collisions have occurred total. So we need to keep track of the number of collisions. That's why we have this num collisions variable as a parameter to handle collisions. Then we have a move guys function. So we're pretty much done with all that collision detection stuff. Let's move on to this move guys function. Move guys is going to go through all of the guys, call their advance method in order to move them forward, and rotate them appropriately and do all that good stuff. Then we call guy moved on the quad tree in order to indicate to the quad tree that the guy has changed his position. After that we have an advance function, which is just going to basically alternate between calling move guys and handle collisions. So it'll call move guys over an interval of time between handle collisions, and then it'll call handle collisions. And we have a make guys function, which is going to just make a vector of num guys, new guys. And it'll do that just by calling the constructor for guy and figuring out the scaling factor for the terrain to pass as a parameter to guy. Then we have a draw terrain function, which is going to draw the terrain. And in the lesson on terrains, the way that we drew it is we had all of this code basically in the draw scene function directly, but we're going to separate it into this separate draw terrain function. So we've basically seen this code already in the lesson on terrains. Then we have a draw num collisions function, which is going to draw that string at the top that indicates how many collisions have occurred. And we're going to be using string streams in order to do this, because we need to get this number of collisions into a string. So we need a string that says collisions colon 500, or however many collisions there are. So we're using string streams, which are C++ classes, and if I scroll up to the top, if you want to use string streams, you need include stream, and we're going to be using an OString stream, output string stream, and using this operator right here, the less than operator, we're going to append to the end of the string stream this string right here, collisions colon, and then we're going to append to the end of it the num collisions variable, the number of collisions. And once we do that, the string stream will have the string that we want. Then we just have to call .str in order to get that string into a string variable, this str. The string class is a C++ class that's sort of the C++ equivalent of a character array, and it behaves a lot like a character array, actually. So this str is a C++ string object. Then over here we're going to do all of the actual drawing. We're going to switch the color to yellow and translate to the top of the screen. We're disabling lighting, by the way, because we just want it to be a solid color, a fixed yellow color. We scale, and we call T3D draw 2D, which will take care of drawing the string using our text drawing functionality. And that's draw num collisions for you. We have some variables over here: the model, all of the guys, the terrain, the camera angle, the quad tree. We have the amount of time until we're next going to handle all of the collisions, and we have the number of collisions that have already occurred. In our cleanup function, we have where we delete the model and delete each of the guy objects. And we're also calling T3D cleanup, which, if you'll remember, this just takes care of disposing all of the resources used by the text drawing functionality. So this function is in text3d.h. Then we have, in init rendering, we have a call to T3D init, which initializes the text drawing functionality. We have right here where we load in the model, and the model is blockybalboa.md2. That's the name of our block, guys, blockybalboa. And if the model isn't null, which means that there was no problem loading the model, we're going to switch the animation to be the run animation. Then we have our draw scene function, which basically just calls some stuff that we've already seen before. So it calls draw num collisions, the function that I showed you. It calls draw for each of the guys, and it calls draw terrain in order to draw the terrain. We have our update function, which increases the camera angle, and calls advance in order to advance the state of all of the guys. In our main function, we have a few things. We have load terrain, which loads the terrain from a particular height map into this terrain variable. We have a call to make guys in order to create all of the guys. We have, right here, we're going to compute the length of the terrain after scaling. So it's just the scaling factor for the terrain right here times the length of the terrain. And that'll give us the length of the terrain after scaling. And we need this in order to construct a new quad tree. So we're going to construct this new quad tree and store it in the quad tree variable. And then we're going to add each of the guys to the quad tree variable. And that's all the stuff we need to do to get everything set up. So this program hopefully should give you an idea. It should crystallize your knowledge of terrains, drawing text, animation, and collision detection.